So today we're going to continue our discussion of power series. Last time we talked about section 11.8, the definition of a power series, finding radii and interval of convergences, and identifying the center, questions about the symmetry of the interval of convergence, that sort of thing. Today I'd like to address a little bit more of those questions of symmetry and possible IOCs. But then I want to move on to 11.9, which is discussing how to find power series representations for a given function. And this is where things start to get a little bit more challenging computationally. This is where you'll start to run into some harder calculations. So first we'll cover a little bit of the concept stuff, and then we'll talk about the calculation stuff. The calculation stuff is going to get a little hairy, but I have faith in you. Another thing I'd like to say before we get any closer to it is what the hell's going to happen for exam 3, right? So exam 3 is going to take place, of course, we must do it. But because we're so short for time, what I'm thinking of doing is a take-home test. So this would, in the online format, the way the take-home test would work is I would post a PDF. You would be required to print the PDF. And then over a period of several days, you will complete the problems there on your own without using any outside resources. And then you will submit the scans of your PDF online. So what I am thinking is that next Friday, a week from this Friday, I will send you the PDF of exam 3. You will be required to print it. You'll answer the questions, and then you will scan with your phone and submit on Canvas. So it won't be timed or proctored, but there will be an honor statement on there that you must sign. And my feelings about cheating are as strong as ever. Even if you did really good all the way through the course, if I suspect you of cheating on the take-home test, I'll string you up brutally and we'll have a trial and everything like that. I don't want to go through that shit, so please don't do it. But it's going to be a take-home test. I will give it to you next Friday, and it will be due on the day of the final. So I just wanted to, in case you're nervous, explain to you what exam 3 is going to be and where it's going to come from and all that good shit. So that is the plan, right? Exam 3 will be a take-home that I will give out next Friday. So with that said, we can begin our discussion. Oh, I see here. I have something in chat I need to address really quick. So right now we need to talk about power series. This is, of course, Calc 2. So today we're going to talk about how to represent functions as power series. First, though, a question. How should I say this? What is the smallest possible interval of convergence for the power series sigma n from 0 to infinity Cn x minus 1 to the n, given that sigma n from 0 to infinity, let's say 3 to the n Cn converges. So this is a somewhat general question, but if you are able to answer this, it will be very helpful on what I think is probably the hardest question in your current homework, and some questions that I often put on exam 3. So I have a power series here. It's centered at 1. And I'm told that this series, which is clearly related somehow to this series, I'm told that this series converges. So first, I'm asking about the interval of convergence. So let's draw a little number line and plop our center, which is 1, right in the middle there. I want to know, how far away from 1 can I wander and still get a convergent series? That's the question of the interval of convergence, right? The interval of convergence always is centered at the center of the series. And then the radius of convergence tells you how far away from that you can walk and still get x values that will give you a convergent series when you plug them in here. Now somehow I need to use this information. So what is the relationship between this series, which I'm told converges, and the power series I was given? In other words, is there a number I can plug in for x here so that this series becomes this series? Well, if this is an x minus 1 to the n, and I've got a 3 to the n here, yeah, this is the same as 4 minus 1 to the n, which is equal to my series, my power series, evaluated at x equals 4. So I'm told that my series converges when you plug in x equals 4. So because this converges, we know that x equals 4 is in the interval of convergence. Okay, well, if this is 1, then 4 is somewhere over here. And I know that this guy is in my IOC. Before then it would be, man, not the same-ish. It would actually be exactly the same, right? Cn times 3 to the n is the same as 3 to the n times Cn. So if you plug x equals 4 in this, you get this. You get this exactly. And that's this statement here. So plugging 4 into this series gives me a series that I know converges, which means 4 has to be in the interval of convergence for my series. So what is the smallest possible radius of convergence? So we want to be careful. Remember, the radius is always measured from the center. Yeah, so the smallest possible radius of convergence is this distance, which is 3. So the radius of convergence has to be at least 3. So the smallest possible radius of convergence is 3 itself. If the radius of convergence were exactly 3, then my interval of convergence would need to be closed on the right, because I know that 4 is in the interval of convergence. And if I can walk to the right 3, then I can walk to the left 3. And if I walk to the left 3 units, I get over here to -2. Which means my smallest possible interval of convergence is -2 to 4. I know I have to include the 4 because that's where I got this information from. I was told. Oh no, Dalton, I promise you, you're not. Plenty of people have those same thoughts. I have to include the 4 because I was told that my series converges at 4. I don't necessarily have to include the 2 though, the -2. So this is a possible IOC for this series because it is symmetric about the center, and the smallest possible radius of convergence is 3 because I know I can wander to the right 3 and still stay in the IOC. If I wander to the left 3, I get over here to -2, but maybe -2 itself isn't included. We've seen that, right? The endpoints can either be included or not included. It depends on the series. And I don't have enough information here to say whether or not the -2 should be included or excluded. So the smallest possible is the left open, right closed interval from -2 to 4. So Simon, the question itself was this. I was told that the series 3 to the n Cn converges, and the way you get this series out of this series is by plugging in x equals 4. If you plug x equals 4 into my power series, 4 minus 1 is 3. So you get the series 3 to the n Cn, and we were told that that is a convergent series. So because this series converges, I know that my series converges when x is equal to 4. Because when x is equal to 4, my power series is this series. That means that x equals 4 is in the interval of convergence, because the interval of convergence is all the x values such that my series converges. Since my series is known to converge when x equals 4, because my series when x equals 4 is this series, 4 has to be in the IOC. If 4 is in the IOC, then the IOC stretches from the center to 4, at least. It might stretch further. But the question I'm trying to answer is, what's the smallest possible interval of convergence? So the smallest possible interval of convergence would be the one that stretches out to 4, but just barely doesn't go any further. And that would mean the radius of convergence is 3. The smallest IOC centered at 1 with radius 3 is the interval -2 to 4. Yes, exactly. Given the information that we have, this is all that we can say about the IOC. The IOC might be much larger, but given the information we have, this is as much as we could say. All right, so I wanted to go through one more like this. We did an example like this at the end of class last time that wasn't quite as explicit. And there is a problem in your homework that will require you to think like this. There will be problems on your tests that require you to think like this also. So let me pull up the relevant homework problem so you can be aware. Yeah, exactly, Ryan. So I don't know. Just because the interval is closed on the right doesn't mean it's necessarily closed on the left. And I don't have enough information to say. All right, this guy, number 8 in your current homework and number 9 in your current homework, both require you to think in this way. Do number 8 first because it's a little bit easier. It's meant to get you ready for number 9. But it's all this sort of thinking. You have to think about the possible IOC. All right. So I'm going to come back here now, and we are going to talk about how to represent functions as power series. This is also where we will learn how to integrate and differentiate power series. So this is the section that tends to be the scariest for people, probably in the whole class. Your homework this week is going to take a long time, so please give yourself a lot of time to do it. In other words, don't expect to go out and have fun this weekend, or today, or tomorrow, or Friday, or early Monday. Everything here begins with what we know about geometric series. Yeah, pretty much. None. No fun. I mean, well, no, that's not true. This shit is fun, right? This is your fun now. So, this guy is a geometric series. Yes. His starting term is 1. His common ratio is x. So this series converges to 1 over 1 minus x as long as the absolute value of x is less than 1. This series, this infinite polynomial over here, is equal to this as long as x is between -1 and 1. I try not to make any such assumptions about people, but I hope. All right. Quick thought. This guy, remember, is the polynomial. It just goes on forever. 1 plus x squared plus x cubed, and so on. So differentiating this thing is easy. I just differentiate each piece according to the power rule. Integrating this thing is easy. I just integrate each piece according to the power rule. All the good shit you want to do with functions is pretty easy to do to this. The graph of 1 over 1 minus x looks like this. It's a rational function. The denominator is 0 when x is equal to 1. So we have a vertical asymptote there, x equals 1. Have a y-intercept of 0, 1. Have a horizontal asymptote, y equals 0. So the graph of 1 over 1 minus x looks like this. There's another branch down here. The graph of my power series then should be the same as this graph, because my power series is equal to this function. However, the graph of my power series just contains the portion from -1 to 1. Over here at -1 is equal to 1/2, at 0 is equal to 1, and we've got our vertical asymptote at +1. And he's actually open here because he doesn't converge at when you plug in -1. So if you take just this portion of the graph of 1/1 minus x, you get the graph of your power series. I don't mean for these graphs to overlap. So here's this one, and here's this one. They're separate, right? So the basic idea is that this function can be represented as a power series like this, as long as you stay between -1 and 1. One over 1 minus x, it's the sum of a geometric series. Starting term over 1 minus the common ratio. This is a geometric series whose starting term is 1 and whose common ratio is x. So the sum of the series is 1 over 1 minus x. So this series is really a function. The graph of the function looks like this. It's the same as the graph of this function, except his domain is restricted because the series doesn't always converge. It depends on what you plug in for x. If you plug something bigger than 1 in for x, the series will diverge. But as long as you plug in something between -1 and 1, you'll get this out, which means the graph of that function and the graph of that series look the same on the interval -1 to 1, on the interval of convergence. In other words, this function can be represented by this series. If I wanted to differentiate this function, I could differentiate this series instead. If I wanted to integrate this function, I could integrate this series instead. If I wanted to do anything with this function, I could do it with this series instead, as long as I keep my x's between -1 and 1. Because the alternating series -1 to the n diverges. It fails test for divergence. That's the easiest way to see it. Okay. So all of our work, I'll say it down here in case anybody is still writing or drawing or adding things here. All of our work in section 11.9 begins with 1 over 1 minus x equals sigma n from 0 to infinity x to the n. This is our crucial fact. And the stuff that we're going to be doing in this series, I will refer to this as the geometric series trick. It's not really a trick, it's just a fact. Okay? So my goal in 11.9 and 11.10 is I hand you a function, you tell me the power series that's equal to that function. And then you also have to tell me where the series converges. In other words, for what values of x does the series converge, or what is the interval of convergence? So let's begin here. What if that is a 3 instead of a 1? Can I find a power series representation for the function 1 over 3 minus x? The trick is to get it into the 1 over 1 minus r form. So I use my geometric series trick. Which is 1 over 1 minus r is sigma n from 0 to infinity r to the n. So I need to write f of x as 1 over 1 minus something. And whatever that something is will tell me what to put in my series. F of x is 1 over 3 minus x. And if I want to write that as 1 over 1 minus something, I need to get rid of this 3. So I can force factor a 3 out from the denominator. This is the same as 1 over 3 times 1 minus x over 3. Does everybody understand that algebra? Force factoring? Alrighty. Now, 1 over 3 times 1 minus x over 3 is the same as 1/3 times 1 over 1 minus x over 3. Because that's how fractions multiply. If I want to multiply this fraction times this fraction, the top is 1 times 1, and the bottom is 3 times this, which is this. Now by my geometric series trick, that's 1/3 times, here, r is x over 3, right? This is 1 over 1 minus r if you plug x over 3 for r. So that's sigma n from 0 to infinity x over 3 to the n. Now, if I want to write this in the normal power series way, I need like Cn times x minus a to the n. So in other words, I need to like clean this shit up a little bit. X over 3 to the n is the same as x to the n over 3 to the n. And this is the same as 1/3 sigma n from 0 to infinity 1 over 3 to the n times x to the n. And that's starting to look like a power series, right? My last step would be to bring this 1/3 in. So right now the 1/3 is out front multiplying the whole series. I can bring it inside because he is a constant. So the 1/3 out front can come inside like that. And then my very last step would be to combine the 1/3 and the 1 over 3 to the n as 1 over 3 to the n plus 1. So this is my answer. We're doing the find the sum of the series backwards. Yeah, you're starting with the sum of the series, which should be the function, and you're finding the series that sums to that function. That's okay. Like I said, the section is hard. Remember, everything revolves around this. 1 over 1 minus r is the same as sigma r to the n. So I take my function and I try to write this as 1 over 1 minus r. For some value of r. That's what will allow me to use my geometric series trick. So right now I've got 1 over not 1 minus x. I want this to be a 1 over 1 minus something. So in other words, I need to make this into a 1. I need to make this 3 into a 1. So I factor a 3 out from the bottom. That gives me this. Now I've got 1 over 1 minus x over 3 if I bring the 1/3 out like that. So this piece right here, I say, just this piece is 1 over 1 minus r with r equal to x over 3. That was my goal. My goal was to get this thing in the form 1 over 1 minus something. So I'm not worrying about this 1/3 at the moment. He just comes along for the ride. But this piece, 1 over 1 minus x over 3, that looks like 1 over 1 minus r. All right, 1 over 1 minus r. 1 over 1 minus r. So this thing is equal to sigma r to the n, where r is x over 3. So the 1/3 out front comes along for the ride, and this piece is this series. Ah, Fernando, you're so goddamn sneaky. Yes, you could do that also. So what Fernando said in chat is correct. We could do it like that. Your series would be centered at 2 then instead of at 0. And sometimes that's a really good move. But what I'm showing you here is the more standard approach, because depending on the constant here, it's not always easy to get a 1 there. Also, we usually like our power series to be centered at 0 unless for some reason we want a different center. So most of the time you will be finding your power series centered at 0. But if you did that on a test, Fernando, I would be absolutely fine with it. There are advantages and disadvantages to both. So, are we comfy with why this piece is equal to this series? This piece equal to this series. And are we comfy with the algebra that got us from here to here? Okay then, so we do the algebra to get from here to here. Then I write this piece as this series, bringing the 1/3 along for the ride out front. And then from there, it's the sort of manipulation that we've been doing. I give the power to both the top and the bottom. Then I bring the 1/3 in. So here I gave the power to the top and the bottom. Then I separated those two pieces because this is my x piece. So this is going to be like my x minus a to the n. And this piece has to do with my coefficients, Cn. And a power series has those two things separated. Then I bring the 1/3 inside, and I combine the 1/3 and the 1 over 3 to the n, using my rules for exponents, multiply the top by the top, the bottom by the bottom. 1 times 1 is 1. 3 times 3 to the n is 3 to the n plus 1. Here my center is a equals 0 because x to the n is the same as x minus 0 to the n, and my coefficients Cn are 1 over 3 to the n plus 1. And if I wanted to find my interval of convergence, I would do all the shit we did in the last video. Run the ratio test, and then check the endpoints. Or, because this happens to be a geometric series, right, all I've used is the geometric series trick, I could set the common ratio less than 1 in absolute value. So to find the IOC, I can either use the ratio test, then check endpoints, or use our theorem on geometric series. I'll do this one because it's faster. The series sigma n from 0 to infinity 1 over 3 to the n plus 1 times x to the n is geometric with r equal to 1/3 x. So it will converge if and only if the absolute value of 1/3 x is less than 1, which is the same as saying, now I unpack, -1 is less than 1/3 x is less than 1, which is the same as saying -3 is less than x is less than 3. That is, or i.e., the IOC is the open interval -3 to 3. I don't need to test the endpoints because it's a geometric series. Geometric series only converge if the absolute value of the common ratio is strictly less than 1. You could check though, if you plug in +3, then you get the series 1 over 3 to the n plus 1 times 3 to the n, which is 1/3 plus 1/3 plus 1/3 plus 1/3 plus 1/3, fails TFD. If you plug in -3, then your series is 1/3 minus 1/3 plus 1/3 minus 1/3 plus 1/3 minus 1/3, which also fails TFD. But if you're just using geometric series, you know your series is geometric, then you don't need to test the endpoints. You can just say the common ratio has to have absolute value less than 1. Questions on this problem? So the common ratio here, easiest to see from this step. Common ratio here is x over 3, because this is x over 3 to the n. Or if you were to write out the terms of this series, you would see that to go from one term to the next, we're multiplying by x over 3, or 1/3 x. So the same way we find common ratios for any other geometric series. That is most of 11.9, yep. Now, Gustavo, the hard part is that we can't always just use the geometric series trick. Sometimes we have to be considerably more clever. So yeah, 11.9 is pretty much find the series, find the IOC. So let me make it a little bit more challenging. Can we find a power series for the natural log of 1 plus x? Focus, you shit. Come on. Come on. All right. Stay. Well, the natural log of 1 plus x, that does not look like something I could write as 1 over 1 minus r, does it? However, This is true. We know this from the early part of the semester. It's a little U sub, but it's a micro U sub. We should be able to spot it very quickly. It's very sneaky. Now 1 over 1 plus x, that's 1 over 1 minus negative x. So the stuff inside the integral here, I can write as 1 over 1 minus r. One over 1 minus negative x here off to the side, that's sigma n from 0 to infinity negative x all to the n, which is the same as sigma n from 0 to infinity negative 1 to the n x to the n. Yeah, it's really cool. So from here, I can say this is the integral of sigma n equals 0 to infinity negative 1 to the n x to the n dx. And this looks intimidating. I acknowledge that. But if you just remember that you can integrate term by term, the only piece here that has an x is this guy. So the integral, which is being done dx, doesn't care about sigma, doesn't care about n's, doesn't care about negative 1. He just cares about this piece. So this is sigma n from 0 to infinity negative 1 to the n times x to the n plus 1 over n plus 1. I've already got my plus c over here from the indefinite integral. So I don't need another plus c here. I've put my plus c on this side at the start. So in other words, what we've just shown here is that c plus the natural log of 1 plus x is equal to sigma n from 0 to infinity. It's equal to this thing. And I'm going to put the 1 over n plus 1 term from the downstairs here separate from the x. So this is negative 1 to the n over n plus 1 times x to the n plus 1. And if I write out the first few terms of this series to get a feel for it, when I plug in n equals 0, I get 1 over 1 times x to the 1. That's x. Then plus 1 to the negative 1 over 1 plus 1 times x squared. That's minus 1/2 x squared. And then I would have plus 1/3 x cubed minus 1/4 x to the 4, and so on. So this infinitely long polynomial is equal to this function for some choice of the constant c. And if we plug in x equals 0, we find that c plus the natural log of 1 plus 0 is equal to 0 minus 1/2 times 0 squared plus 1/3 times 0 cubed minus 1/4 times 0 to the 4, and so on. All this shit is 0. So we get c plus the natural log of 1 is equal to 0. But the natural log of 1 is also 0. So C is equal to 0. In other words, the natural log of 1 plus x can be represented as the power series n from 0 to infinity, negative 1 to the n over n plus 1 times x to the n plus 1. And this is how I knew that the natural log of 2 was equal to the alternating harmonic series. We talked about that last week. This is an important series. This is not just an example for today, but it's something you need to commit to memory forever. What we did here is we integrated a power series. I'm going to give you a theorem that shows you in general how we integrate power series and what the result is on the radius and interval of convergence. And I'll also tell you what happens when you differentiate a power series and how that affects the interval and radius of convergence. But what we did here in this example is characteristic of the normal thing. You just integrate the x piece because your integral is being done dx, which means all this shit is constant with respect to the integral. The integral doesn't care about anything except for the x's. So I recognize if this example feels a little bit over your head right now, that's okay. It's the very first one we've done like this. Let me give you the theorem and then we'll come in and try a few more, okay? Does everybody have all of these pieces down in their notes? I'll give just a few minutes for anybody who's still writing. Yes, I just integrated x to the n. So I add 1 to the power and divide by the new power. It's a power rule integral. It's super easy. As an integral, it's super easy. But it looks really scary in this notation, doesn't it? When you see all those movies that have like famous mathematicians or physicists and they show like integrals and sigmas floating around, they always do it like this to try and make it look as scary as possible. But this piece is just a big long polynomial. You're just integrating a polynomial. So it's really not that bad. Add 1 to the power, divide by the new power. Yeah, the notation looks frightening, but it's none of the machinery is frightening. Staring is okay, writing is better. So if we want to get more comfy with this stuff, we need to write more. Integration and differentiation of power series. I have for you 2 theorems. If f of x is sigma n from 0 to infinity Cn times x minus a to the n has radius of convergence r, then the integral of f of x, which is the integral of this series, is equal to an additive constant plus the sum from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1. So you add 1 to the power and you divide by the new power. The x minus a thing is a micro u sub. Yeah, practice. Practice more than staring. you're really just integrating a polynomial. This also has radius of convergence R. So the radius of convergence doesn't change. The IOC can actually change. You can pick up an endpoint when you integrate, but you'll never change the size of the interval. Proof. The integral of f of x is the integral of sigma n equals 0 to infinity cn x minus a to the n dx is the integral of, now I just write out the terms of the series, c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed plus and so on dx. Now I make the u substitution or the z substitution. I let z be x minus a so that dz is dx. It's an indefinite integral, so no bounds to change. And I get integral c0 plus c1z plus c2z squared plus c3z cubed and so on, done dz. And then I split the integral up. I do one integral for each term, integral of c0 dz plus integral of c1z dz plus integral of c2z squared dz plus integral c3z cubed dz and so on. Cn is the nth coefficient in the series. So Cn is the number that multiplies x minus a to the n in the series. So in other words, if I write this series out without the capital sigma, I get this stuff in the brackets here. So it's not like modified by n, that's not the word I would use, it's the nth coefficient. But now, the integral of the constant c0 is c0z. The integral of c1z is c1 times 1/2 z squared plus c2 times 1/3 z cubed plus c3 times 1/4 z to the 4 and so on. And then we go back to our original variable. This is c0, z is x minus a, plus c1 times 1/2 times x minus a all squared, plus c2 times 1/3 times x minus a all cubed, plus c3 times 1/4 times x minus a to the 4 and so on. And this is sigma n from 0 to infinity Cn times 1 over n plus 1 times x minus a to the n plus 1. And then we just tack our big additive constant out front from the indefinite integral. So if I wanted to, I could write this as c, like a plus c out here, a big plus c. And that's the proof. The integral of f of x is this formula, the formula that I gave you in the theorem, with an additive constant. And usually we like to write this additive constant out front so people can tell that it's not inside the series. So as my last line here, I would say, which is equal to C plus sigma n from 0 to infinity Cn 1 over n plus 1 x minus a to the n plus 1. Well, we used this in the last example problem where we had to find a power series for the natural log function. This is the theorem that we were using. I did the integration term by term there, and that's all this says, is that you can integrate term by term. The other thing we need to show is that the radius of convergence hasn't changed. IRL, there's lots of reasons you need a power series IRL. Physicists use them for approximations all the time. Anytime you need to do anything with a function that's hard to work with, you want to write it as a power series. And oftentimes, the easiest way to get something as a power series is to integrate something else. I'll show you several real-world examples when we get to 11.10. One is finding the length of an orbit. Like how long is the orbit that the Earth takes around the sun? You need to do an integral like this to get it. All right, so the radius of convergence doesn't change because of the ratio test. L is the limit as n goes to infinity of an plus 1 over an, which is the limit as n goes to infinity of Cn plus 1 times 1 over n plus 2 times x minus a to the n plus 2, all divided by Cn times 1 over n plus 1 times x minus a to the n plus 1, which is equal to the limit as n goes to infinity of absolute value Cn plus 1 over Cn times, I'll flip and multiply here, and I get n plus 1 over n plus 2 times, here I just have x minus a to the n plus 2 over x minus a to the n plus 1. That's just x minus a, which is equal to lim n to infinity absolute Cn plus 1 over Cn times absolute n plus 1 over n plus 2 times absolute x minus a. This x minus a can come out front the limit. And this piece goes to 1. So this is abs x minus a times lim n to infinity Cn plus 1 over Cn, which is the same as L for the original series. Sigma n from 0 to infinity Cn x minus a to the n. So the ratio test, when applied to my new integrated series, simplifies to this. And this is what I would get if I applied the ratio test to the original series. So the radius of convergence for my new series has to be the same as the radius of convergence for my original series. Because the ratio test limits are the same. Since L for the new series equals L for the old series, the ROC is the same for both. All right, so that's the theorem. That's the proof. So you can integrate a power series as though it is a polynomial. That's the idea. You can integrate a power series the same way you integrate a polynomial. And if you're having a hard time seeing it in sigma notation, write it out in the long ... notation. Here's the piece you absolutely must remember. All right. So if your notes have gotten a little bit cluttered as we went through that proof, take 10 seconds here and write this down nice and clear somewhere. The integral of this series is equal to this. And the radius of convergence of the result is the same as the radius of convergence of the original. So make sure this is nice and clear somewhere in your notes. Someone wanted to see the last few lines of the proof there. So remember, what we're proving in this last part is that the radius of convergence doesn't change when you integrate. So I look at the ratio test limit for my new series, and I find that the ratio test limit L for my new series, which simplifies to this, is exactly the same as the ratio test limit for my original series. If I applied the ratio test to this, it would immediately simplify to this. So L for my new series is the same as L for my old series, which means that the radius of convergence has to be the same for both because they have the same ratio test limit. I'm going to put this back up for a second. Here, I'll do it like this. Let me zoom out a little. Okay. So again, this is the piece that you must remember. Specifically this. The integral of that power series on the top of the blue box is the same as the power series on the bottom of the blue box. So when you integrate a power series, you just add 1 to this power and then divide by that new power. Also, you tack a plus C out front. And remember that the radius of convergence doesn't change. A note is that while the radius of convergence doesn't change, the interval of convergence can change a little bit. So Simon, the answer to your question is here. If you're having a hard time seeing it, go ahead and run the ratio test on this. If I run the ratio test for the original, that's L equals lim n to infinity an plus 1 over an, which is lim n to infinity cn plus 1 x minus a to the n plus 1 over cn x minus a to the n, which is limit n to infinity abs cn plus 1 over cn times x minus a to the n plus 1 over x minus a to the n, which is lim n to infinity abs cn plus 1 over cn times abs x minus a, which is x minus a lim n to infinity cn plus 1 over cn. So this is the old ratio test limit. This is the new ratio test limit, and they're the same. Okay, I don't want to get too far away from what we need to be doing here, which is building skills. So one more practice problem where we integrate power series, and then I will show you how to differentiate power series. You guys know I love the arctangent function. Yeah, this is all section 11.9. All right. So just like in the last problem, I know that the integral of 1 over 1 plus x squared, here I've got 1 over 1 plus x squared, I know that that's the inverse tangent of x plus c. And I also know that 1 over 1 plus x squared is 1 over 1 minus negative x squared, like this. Careful with your parens. If you put the square on the outside of the paren, it's wrong. So now, according to my geometric series trick, this is 1 over 1 minus r, where r is negative x squared. So what I'm going to do to get arctan is integrate this series. This series is equal to 1 over 1 plus x squared, and the integral of 1 over 1 plus x squared is arctan. But before I can integrate this series, I need to write it in the form that matches my theorem. Right now, where did I put that? So I need to write it in the Cn x minus a to the n format. Right now it doesn't look like that. So first you must simplify your series before you can integrate or differentiate. I get sigma n from 0 to infinity. Sorry, my sigmas tend to be a little bit straight in the middle. Negative x squared all to the n is negative 1 to the n times x squared to the n, which is the same as sigma n from 0 to infinity, negative 1 to the n times x to the 2n. Rules for exponents, right? Just simple algebra stuff here. So first I use my geometric series trick. I want to write this as 1 over 1 minus r. So that's 1 over 1 minus negative x squared. So r is negative x squared. So this is sigma n from 0 to infinity, negative x squared to the n. Negative x squared is negative 1 times x squared. So if I raise all of that to the n, that's negative 1 to the n times x squared to the n. And then x squared to the n is x to the 2 times n. That's one of your rules for exponents, like a to the b, all to the c is a to the b times c. Now this I can integrate. That's looking like something that my theorem would recognize. The integral of this power series, I just add 1 to the power and divide by the new power. I also remember to bring my plus c and I write it out front. I'll have negative 1 to the n times 1 over 2n plus 1 times x to the 2n plus 1. Add 1 to the power, divide by the new power. So I know that the inverse tangent function is equal to c plus sigma n from 0 to infinity. I'll write this as negative 1 to the n over 2n plus 1 times x to the 2n plus 1, just to make it look prettier. And if I plug in x equals 0, we should be careful. Let me write this out long form. This is c plus, when n is 0, I get x. Then when n is 1, I get minus 1/3 x cubed. Then plus 1/5 x to the 5. Minus 1/7 x to the 7, and so on. So now plugging in 0, I find that the inverse tangent of 0 is c plus 0 minus 1/3 times 0 cubed plus 1/5 times 0 to the 5. Next term would be minus 1/7 times 0 to the 7, then plus 1/9 times 0 to the 9, but all those are 0. Do me a favor. I'm going to say this out loud real clearly. Anytime you plug a number into a power series, write the damn series out. Don't go plugging 0 into expressions that look like this. Plug 0 into expressions that look like this. If you plug 0 into expressions that look like this, I will be able to trick you with something on a test. There will be problems in your physics classes and in your real life experiences, if you ever need power series in them, where doing that will bite you in the ass. Anytime you go to plug any number into a power series, do yourself the favor of first writing out the series like this. Having written the series out like this, I can plug in 0 and be confident that every single term is actually 0. On the other hand, the inverse tangent of 0 is 0, so I get 0 equals c plus 0. So again, c is 0. So the inverse tangent of x really is sigma n from 0 to infinity, negative 1 to the n over 2n plus 1 times x to the 2n plus 1. And this is another super important series that you need to remember forever and ever, amen. Just like the natural log series from the previous example, this is one to tuck in your pocket. There are going to be 5 or 6 of these series that I require you to know by heart. The 2 that we've done as examples so far are some of the most important. Okay. The place we started with this series is by recognizing, the place we started with this problem is that we remembered that arctan can be written as this integral. If we didn't know this at the start, then this wouldn't work. Nas 1 over 1 plus x squared is not the series in the box at the end, that's arctan. 1 over 1 plus x squared has this series representation, this guy. This blue box here is equal to 1 over 1 plus x squared. Right, period here. So 1 over 1 plus x squared is this, which means the integral of 1 over 1 plus x squared is the integral of this, which is what I have here. But the integral of 1 over 1 plus x squared is arctan. So arctan is equal to that integral. So there's kind of 2 steps here, 3 steps here, really. First, I remember that 1 over 1 plus x squared can be integrated to get arctan. So I want arctan. I need some way to get a series for arctan And if I remember that arctan is the integral of 1 over 1 plus x squared, I go, oh, sweet. So I can find a series for 1 over 1 plus x squared, integrate that, and that will give me a series for arctan. So our first step is to just remember that arctan can be gotten as the integral of 1 over 1 plus x squared. Then I find a series for 1 over 1 plus x squared. And then I say, okay, I've got a series for 1 over 1 plus x squared. And I know that if I integrate 1 over 1 plus x squared, I get arctan. So I integrate. And I know that the result here is arctan, because this integral is arctan. I've just got my plus c on that side. Then I solve for c. So those are the kind of steps here. I'm dead in the water if I don't remember this. So just remembering the basic integrals from the start of the semester is very important for all these problems. Once I remember this, I've got a path I can start chasing. Yeah, I would actually recommend spending several hours a day on this. You know, an hour and a half is not bad, but I would shoot for something more like 3 hours a day. It's hard and it takes a lot of time. It's easy to underestimate the amount of time that's necessary to spend here. I do my best to be like gentle in the way I say things and helpful and stuff, but at the end of the day, it's a lot like training for athletics or something like that. You really, really, really need to put in the time. Yeah, a nice way to do that is to break it up. You know, do a chunk in the morning and a chunk in the evening. I remember when I was doing this stuff, what I would do is in the morning, I would get up, make my coffee, and then I would usually go meet up with a friend from class or something like that, go somewhere where I wasn't so distracted and burn a bunch of time. And then I would come home and do whatever I needed to do. And then while I was eating my dinner, you know, I would sit down and solve a few more problems. And that way you manage to put a lot of time in a day without feeling super overwhelmed. All right, we're getting close to the end of class, so I need to show you how to differentiate power series. We've done a couple examples with integrating power series. We need to see how to differentiate them as well. So I'll give you the theorem, and then we'll do an example. If f of x can be written as the power series sigma n from 0 to infinity cn times x minus a to the n, then f primed of x can be written as the series sigma n from 1 to infinity cn times n times x minus a to the n minus 1. And the radius of convergence is the same for both. All right. So again, it kind of looks how you would expect it to look. I just differentiate this piece and forget about everything else. So I reduce the power by 1, n goes to n minus 1, and I bring the power, the original power, down. So the derivative of x minus a to the n, imagine there's no sigma there, is n times x minus a to the n minus 1. So really it's saying you can pretty much forget about the sigma. The catch here is that my lower bound has changed from 0 to 1. And the reason for that is that the constant term in this series differentiates to 0. So a quick proof and an example. if f of x is sigma n from 0 to infinity cn times x minus a to the n, that is c0 plus c1 times x minus a plus c2 times x minus a squared plus c3 times x minus a cubed, and so on. So f primed of x is what I get by priming this whole thing. C0 plus C1 times x minus a plus C2 times x minus a squared plus C3 times x minus a to the 3, and so on, all primed. So now I just prime each piece. The derivative of C0 is 0, because it's a constant. The derivative of C1 times x minus a, this is a chain rule thing, right? So x minus a to the 1 has derivative 1. So this is just C1 plus C2 times the derivative of x minus a squared is 2 times x minus a to the 1. And then by the chain rule, you would multiply by a 1 from the inside. Plus the derivative of C3 times x minus a cubed is C3 times the derivative of x minus a cubed, which is 3 times x minus a squared times 1 by the chain rule. Right, if you want, you can think of this C1 times 1. And so on. So what is this? This is C1 plus C2 times 2x minus a plus C3 times 3 times x minus a squared plus, follow the pattern. The next term would be C4 times 4 times x minus a cubed. And the general pattern here, you've got a sigma Cn times n times x minus a to 1 less than that, which is n minus 1. The catch here is that there's no n equals 0 term anymore. The n equals 0 term went away. He differentiated to 0. So instead of starting at 0, my series now starts at 1. So the rule, that's it. This is the proof. The fact that the radius of convergence doesn't change comes from the ratio test. L is the limit as n goes to infinity of abs an plus 1 over an, which is the limit as n goes to infinity of abs cn plus 1 times n plus 1 times x minus a to the n plus 1 minus 1 is n over n minus 1 plus 1, yeah, over Cn times n times x minus a to the n minus 1, which is equal to the limit as n goes to infinity of abs Cn plus 1 over Cn times n plus 1 over n times x minus a to the n over x minus a to the n minus 1 is just x minus a. Pop out the absolute value of x minus a, you get lim n to infinity abs Cn plus 1 over Cn times abs n plus 1 over n. And again, this piece goes to 1. So you get x minus a lim n to infinity abs Cn plus 1 over Cn, which is the same as the ratio test limit for the original series. Therefore, the ROC doesn't change. All right. So the proof that the ROC doesn't change is very similar for the integral and derivative. I don't want to spend a whole lot of time talking about that because I do want to do at least one example. the catch here, the only thing, so the thing that you must remember is the theorem itself. I'll zoom out so you guys can, if you're still writing for the proof, you can still see it. The thing that you absolutely must remember is this, right? Just like for the integration theorem, the proof is great. You know me, I love proofs. Proofs are good. But this class, we're mostly concerned with your calculation skills. So you must know how to use the theorem. This is how you use the theorem. So make sure this is somewhere nice and clear in your notes. An example. I said the hardest problem in your homework was that conceptual one about intervals of convergence. But the problem that's going to take you the longest is the one that's similar to this. I strongly advise that you do it exactly as I'm doing it here. 1 over 1 minus x all squared looks like the derivative of something. It looks like the result of differentiating something like 1 over 1 minus x. Right, this is the same as 1 minus x to the negative 2. So I say f of x looks like what I'd expect to get from priming something like 1 over 1 minus x. Because that's the derivative of 1 minus x to the negative first. Now, if I actually take that derivative, it's a chain rule, power rule thing. So the chain rule is necessary because it's a composite function, and the outer thing here is a power rule. So this is negative 1 times 1 minus x to the negative 2. And then by the chain rule, I get the derivative of 1 minus x, which is negative 1. So in fact, this is exactly negative 1 times 1 over 1 minus x all squared times negative 1. It's exactly what I want. It's 1 over 1 minus x all squared. The problem like this in your homework that I'm thinking of, that I expect will take you the longest, hurry up, you son of a bitch, is number 12. So you're going to say, this looks like what I would get from the derivative of 1 over 10 plus x. Then you calculate the derivative of 1 over 10 plus x. It won't be perfect, but it will be close. If you do what I did here, just with the function they gave you instead, it will work out. So now, my function, f of x, I know to be the derivative of 1 over 1 minus x. That's what we discovered in the line above. This is similar to the step where I said, oh, arctan is the integral of 1 over 1 plus x squared. Here I'm saying my function is the derivative of 1 over 1 minus x all squared. Now I have a calculus operation that I can apply to something I know how to find a series for to get my function. 1 over 1 minus x, that's a simple geometric series. So in other words, my goal here is to differentiate the series 1 plus x squared plus x cubed, and so on. The 1 differentiates to 0, the x differentiates to 1, the x squared differentiates to 2x, the x cubed differentiates to 3x squared. And if I want to write this in sigma notation, I have nx to the n minus 1 summed not from 0 now, but from 1, because the n equals 0 term differentiated to 0. And that's it. That's the end of this problem. Now here's the rule. When differentiating power series, we don't always change the starting index from a 0 to a 1. We don't always bump the starting index up. When differentiating power series, we bump up the starting index if and only if the original series has a constant term. So here, my original series had this constant term at the start, 1. That's the term associated with n equals 0. And that term differentiates to 0, which is why I bump up the starting index. So when differentiating power series, sometimes we bump the starting index, sometimes we don't. In the theorem I gave you, we do bump the starting index because this most general form of the power series does have a constant term. The starting term here is C0 times x minus a to the 0, which is C0, is a constant, has no x's. So in this theorem, we bump the starting index from n equals 0 to n equals 1, just like we did when solving this problem. But you won't always do that. The only time you must do that is if your series has a constant term at the start. So you should check that first. In other words, write the series out, yeah? Just like before you go plugging things in, you should write the series out. Anytime you're working with a power series, you should at least once write out the first few terms of the series to give yourself a feel for what's going on. Does it or does it not have a constant term? That's the question here. Before, the question was, well, what happens when I plug in 0? Are all the terms 0? And there are other questions like that that we want to be able to answer with confidence. So always write out the series to determine whether or not you should bump the index or not. Okay, that's all the time we have for today. I am going to switch over to my office hours. So if you guys want to talk some more, you can come meet me there. Otherwise, I will see you on Friday when we're going to talk about other tools for finding power series, namely Taylor's theorem. Remember what I said at the end of class last time? You should read 11.8 and 11.9 in the textbook on your own. I can teach you this stuff and it's good, but the book is really good too. So just like in any other class, don't expect to do well without reading. Please read the book. It will help you. Just like I said, you should read 11.8 and 11.9 for today. Read 11.10 for Friday. If you look at it ahead of time, it will be much less scary when we get into it together. So it's nice to have seen it once before. So I would suggest that you read 11.10 for Friday's lecture. If you haven't done, read 11.8 and 11.9, and then consider maybe rewatching this lecture after having done that. It will be helpful. All right. So I'll either see you guys in office hours or I'll see you in class on Friday. I hope you have a lovely afternoon. And that is it. Take care.